This is a cartridge, the type of ammunition used in most small arms. It consists of a metal case, a bullet, a powder charge to drive the bullet, and a primer in the base to start the powder burning. A sharp tap with a pointed instrument will explode the primer, ignite the powder charge, and drive out the bullet. To control this powerful explosion and direct the bullet toward a target is the purpose of all small arms weapons. The term small arms includes shoulder weapons, hand weapons, machine guns mounted on ground tripods, on vehicles, and planes. Some are comparatively simple. Others are complex. But there is a basic similarity which runs through them all. Since they all fire the same type of ammunition, they all function in the same general way. In all of them, a cartridge is placed in the barrel and fired. The empty case is then removed to make room for the next cartridge. This process is called the cycle of operation, and every small arms weapon contains the mechanical means of performing it. To explain this cycle, let's construct a model weapon. It will not resemble any particular weapon, but it will include all of the basic features needed to perform the various individual steps in the cycle of operation. We'll start with a barrel. Removing the top half of the barrel, we can see inside. In the breech end is the chamber. This is where the cartridge fits and where the explosion occurs. Placing the cartridge in the chamber is known as chambering. A sharp tap on the primer would explode the powder charge and drive the bullet out. The same explosion would also drive the case backward out of the chamber. Therefore, the cartridge case must be held in the chamber, so most of the explosion will propel the bullet. The part which backs up the cartridge is usually known as the bolt. One end of this bolt fits against the rear of the cartridge and holds the case in place when it's fired. In order to hold the bolt in position, we need something to support it. The barrel, too, must be held in position. The piece supporting them is known as the receiver. There is a channel in which the bolt can slide. The barrel is attached to the front end. With this side section removed from the receiver and the bolt back, we can still chamber a cartridge by moving the bolt forward. This takes care of the first step of the cycle of operation, chambering. Instead of depending entirely on the weight of the bolt to hold in the case when the cartridge is fired, we'll use some way of locking the bolt in place. The simplest way of locking is to fasten a lug to the side of the bolt. A notch is cut in the side of the receiver. When we close the bolt, we can turn it so the lug fits into the notch and the bolt is securely locked. This is the second step of the cycle of operation, locking. It can be made easier by adding a handle to move the bolt. The handle can also be used to strike this stop. This prevents the bolt from sliding out of the receiver. With the bolt closed, how are we going to fire the cartridge? To fire the cartridge, we must strike the primer. However, the bolt is in the way. Apparently, we'll have to go through it. This bolt was prepared for that. The top half can be removed. It has a channel running through its entire length. All that is needed is a rod to reach from one end to the other. This rod is called the firing pin. You'll notice that it is slightly longer than the bolt, so its point will extend a little beyond the face of the bolt. We can now strike the primer by driving the firing pin forward. One way to drive the firing pin is by using a spring. We've put the spring around the firing pin with one end against this stop. The other end is braced against this shoulder in the bolt. Now when we pull back the firing pin, the spring is compressed. When we release the pin, the spring drives it forward against the primer. This is one way of accomplishing the step known as firing. However, it's awkward to pull back the pin and release it by hand each time we want to fire. We need a means of holding the pin back until we're ready to fire. This is known as cocking. Supposing we put a hook or tang on the rear end of the firing pin. We can still pull the pin back and release it by hand. Now we'll rig up something to hook it onto. But first, we'll have to add a block to the receiver to hold the parts we'll need. The first part is a latch-like piece known as the sear. If we hold it here, under the firing pin, we can catch the tang of the pin when it's drawn back. We'll mount the sear on this pin so that it will pivot freely. We can release the firing pin by pushing down the front or nose of the sear. This is where the trigger comes in. It's mounted on this pin underneath the sear. The trigger can now pivot back and forth. When the trigger is squeezed, it moves the rear end of the sear up. The nose of the sear moves down, and the firing pin is released. Once the sear is lowered, we have to move it back up to catch the firing pin the next time it's pulled back. That's why we need a spring, a sear spring, to push the sear up. It's installed underneath the sear. Now, when we squeeze the trigger, we lower the nose of the sear until it releases the firing pin. Then, when we let go of the trigger, the spring raises the sear nose so it will catch the firing pin when it comes back. The spring also returns the trigger to its original position. We no longer have to cock the firing pin by hand. As the bolt is opened, we can cock the weapon at the same time. The firing pin tang cams the nose of the sear down, and the sear snaps back up. As the bolt moves forward, the sear catches the tang and holds it, and the piece is ready to fire. That takes care of the step known as cocking. Now we have a basic firing mechanism similar to that used on a number of small arms weapons. But there is also another kind of firing mechanism. Some weapons use a hammer, which strikes the firing pin. We'll build this hammer type of firing mechanism on the model. First, let's attach the hammer so it can pivot and strike the firing pin. The spring was taken from around the firing pin to drive the hammer. The firing pin is retracted by various methods in different weapons, and it remains in the rear position until the weapon is fired. To guide the spring, a rod is run through it. The front end of the spring is braced against this shoulder. The rear end of the spring is braced against this supporting block. The rod is attached to the hammer so that the spring pushes against the hammer. When the hammer is pulled back, the spring is compressed. Then the spring drives the hammer forward against the firing pin. To cock this firing mechanism, we can use the same sear, trigger, and sear spring that we used before. When the hammer is pulled back, the sear snaps up into this notch and the weapon is cocked. When the trigger is squeezed, the nose of the sear slips out of the notch and the hammer is driven forward against the firing pin. This mechanism, like the other one, can be cocked simply by opening and closing the bolt. Squeezing the trigger fires the cartridge and sends the bullet out through the muzzle. But it also leaves us with an empty case in the chamber. Before we can get at the case, we have to perform the next step in the cycle of operation: unlocking. We still have the problem of removing the empty case from the chamber. This is known as extraction. On a real weapon, extraction is a serious problem. When a cartridge is fired, the case expands until it's tightly wedged in the chamber. We need something to grip the case firmly and extract it when we open the bolt. The part which does this job is known as the extractor. It has a hook to grip the extracting groove in the head of the cartridge case. The extractor is attached to the front end of the bolt. As the bolt is closed, the extractor snaps into the extracting groove in the head of the case, and it retains its grip as the bolt is locked. Now, when we open the bolt, the extractor pulls the case out of the chamber. Our next problem is ejection, getting the empty case out of the receiver. Notice how the case is held by the extractor. If we pry under the case on the side opposite the extractor, we can eject it from the receiver. If we take a slice off the edge of the bolt, we can get at the case more easily. Now we'll build an ejector in the side of the receiver. It consists of a small lever and a spring. We'll attach the lever so it pivots at one end with the other end held outward by the spring. When we push the bolt forward, the ejector is moved into the side of the receiver. When the case is extracted, the ejector slides into the notch, strikes the case, and ejects it. Let's watch it again. Our weapon is almost complete, but we still have to feed the cartridges to it one at a time by hand. The actual chambering of the cartridge is satisfactory. The bolt moves it forward and it enters the chamber. But once the weapon is fired and the empty case ejected, we want another cartridge waiting ready to be chambered. In other words, we want some method of feeding. There are several ways we can get feeding: by placing a clip of cartridges in the receiver, by using an ammunition belt, or by using a magazine. We'll use a magazine. One side is transparent, so we can see what's going on. Inside is a spring and this follower. As the cartridge is put in from the top, the spring is compressed. As the next round is inserted, the first one is pushed down and the spring is further compressed. The spring, of course, keeps pushing the cartridges against the top. But these lips prevent them from being pushed out. A cartridge can be removed only by sliding it forward like this. And once it is removed, the spring feeds the next one up into position. Now let's install the magazine into the receiver. The magazine is placed so that the top cartridge pushes against the underside of the bolt. When the bolt is opened, it slides back until the face of the bolt clears the rear of the cartridge. Then the cartridge is fed up into the path of the bolt. As the bolt comes forward, it strips the cartridge from the magazine and chambers it. And the spring in the magazine moves the next cartridge up into position. Now, each time the bolt is opened, a cartridge is waiting to be chambered. That's the last step in the cycle of operation, feeding. Our basic weapon is complete. It will perform all 8 steps of the cycle of operation. Let's take them in sequence. First, there's chambering, placing the cartridge in the chamber. Next is locking, securing the bolt in place behind the cartridge. Then firing, squeezing the trigger so the firing pin will fire the cartridge. Unlocking, freeing the bolt from the barrel. Next, extraction and ejection, withdrawing and throwing out the empty case. At the same time, cocking, preparing the firing mechanism to fire again. And feeding, placing the next round in position for chambering. Then the cycle starts over again. These are the 8 steps any small arms weapon must perform each time it fires a cartridge. The steps may not always come in exactly the same order, and the means of performing them may vary. But regardless of the type of weapon, all 8 steps will be performed. And once you know the cycle of operation, you've come a long way toward understanding any small arms weapon. A manually operated weapon will fire each time the bolt is operated and the trigger is squeezed. It's an effective weapon, but its rate of fire is limited. It can fire only as fast as a man can open and close the bolt. However, the rate of fire can be greatly increased by using the force of the explosion to operate the bolt. When a cartridge is fired, a very high gas pressure is built up inside the case. This pressure pushes the bullet out through the barrel and also pushes in all directions. 3 ways have been developed to use this force to operate the bolt. The first way is by gas operation. If some of the gas is tapped off to operate the bolt, we get a gas-operated weapon. By using a model, we'll build up a typical gas-operated weapon. When a weapon is fired, the bullet is moved through the barrel by the expanding gas. To tap off some of the gas behind the bullet, we'll drill a hole in the barrel. This hole is called the gas port. Now, when the bullet passes the gas port, some of the gas will escape through the port. To make use of this gas, we'll direct it into a gas cylinder. Inside the gas cylinder, there is a piston which can move back and forth. When the gas from the explosion escapes through the gas port, it strikes this piston and drives it to the rear. To transmit this rearward movement of the piston to the bolt, we'll have to connect them. A part like this, called an operating rod, will do the job. The rod is mounted with one end attached to the piston. It passes through the gas cylinder and the other end is attached to the bolt. The operating rod has a slot to unlock the bolt. When the piston is forced back by the gas, it moves the operating rod. The operating rod moves back alone a short distance before opening the bolt. This gives the bullet time to leave the barrel, and when the bolt opens, no dangerous gas will escape to the rear. The rod moves back, and the slot cams the lug up and unlocks the bolt. As the movement continues, the rod pushes the bolt open. But that is only half the job. The bolt has to be closed again. One way to close it is to use a spring. We've placed the spring between the piston and the back end of the cylinder so that it is compressed with the bolt open. When the spring expands, it forces the piston forward, which pulls the operating rod forward and closes the bolt. Now let's see the whole action when we fire a round. Some of the gas escapes into the cylinder, driving the piston to the rear and compressing the spring. At the same time, the bolt is unlocked and then opened. Then the return spring takes over and forces the bolt forward. The force of the explosion has been harnessed, so it does all the work of operating the bolt, and we have a gas-operated weapon. Gas-operated weapons, such as the BAR or the M1 rifle, can always be identified by a gas cylinder somewhere under the barrel. The second way of using the power of the explosion to operate the bolt is called blowback operation. As the expanding gases drive the bullet out through the barrel, they also push the cartridge case back hard against the face of the bolt. If this pressure is used to blow the bolt open, we have a blowback operated weapon. Let's build this type of operation on our model. To permit this blowback pressure to work on the bolt, let's remove the locking lug. Now we'll have to fill up this notch and install a guide lug on the bolt. Now, when the weapon is fired, the bullet moves through the barrel and the bolt begins to open. However, the bullet leaves the barrel before the heavy bolt has opened enough to let any dangerous gas escape to the rear. To close the bolt, a return spring is again the simplest solution. We've attached the spring so that one end is braced against the receiver. The other end pushes against the bolt, and when the spring expands, it closes the bolt. Now, let's see what happens when we fire a round. The bullet leaves the barrel before the bolt opens. As the bolt opens, the return spring is compressed. Then the spring expands and closes the bolt. Once again, we've used the power of the explosion to do all the work of operating the bolt. But blowback operation is used only with low-pressure cartridges, because high-pressure cartridges would require a very heavy bolt. Weapons of this type, such as the M3 submachine gun, can always be identified by one simple feature. There is no positive locking device on the bolt. The third way of using the gas to operate the bolt is called recoil operation. As you know, most weapons recoil or kick against the shoulder of the man firing. If we use this movement to operate the bolt, we'll have a recoil-operated weapon. To harness this recoil and put it to work, the weapon is placed inside a stationary housing known as the receiver. The part originally called the receiver now becomes the barrel extension. The barrel extension, and bolt are locked together and are free to slide in the receiver. Now the trick is to use this rearward movement to unlock and open the bolt. Let's first lengthen the locking lug to make it extend beyond the barrel extension and attach a catch. Now, to unlock the bolt, we need some way of pulling this catch down. This cam will do the job. It has a camming slot which fits over this lug on the catch. The cam is fastened to the stationary receiver. Now, when a round is fired, recoil sends the barrel extension, and bolt to the rear. At the same time, the catch is cammed down and the bolt is unlocked. The barrel extension strikes the receiver, stops, and the bolt continues to the open position. To move the barrel extension, and bolt forward, we'll again use a spring. With the bolt open, the spring is compressed. One end pushes against the bolt. The other end is braced against the receiver. When the spring expands, it first closes the bolt, then pushes the barrel and the barrel extension forward. Let's watch the action again. As the bullet moves out of the barrel, recoil begins. It drives the barrel and barrel extension back, and the bolt is unlocked. When the barrel extension is stopped, the bolt continues back. When the bolt is fully opened, the return spring takes over. It first pushes the bolt closed. Then the catch slides up the slot and locks the bolt. The return spring continues pushing until the barrel and barrel extension have reached the forward position. Recoil operation is used on such weapons as the pistol and machine guns. If you see the barrel of a weapon moving back and forth inside the receiver during firing, you can be sure it's recoil operated. Remember, there are 4 types of operation: manual, and the 3 types that use the force of the expanding gas. The gas-operated weapon taps off some of the high-pressure gas behind the bullet to unlock and open the bolt. The blowback-operated weapon uses the rearward force of the explosion to open the bolt. And the recoil-operated weapon uses the kick caused by the explosion to move the barrel and barrel extension back, unlocking and opening the bolt as it goes. These are the basic principles of types of operation, and here we can see how they are used to give plenty of firepower to small arms weapons. Some small arms weapons fire semi-automatically. Some fire automatically. And some can fire both ways. Weapons giving automatic fire will fire continuously as long as pressure is applied to the trigger or until the ammunition is exhausted. This permits spraying of a target with a continuous stream of fire. Weapons designed to give semi-automatic fire deliver only a single shot each time the trigger is squeezed. Thus, each round can be individually aimed. These various types of fire require different firing mechanisms from those used on manually operated weapons. Let's look at a typical firing mechanism for a manually operated weapon to see why it won't work with a bolt that moves back and forth automatically. It's a hammer-type firing mechanism. As the bolt is moved to the rear to cock the weapon, it pushes the hammer back. Squeezing the trigger releases the hammer to fire the round. The bolt is moved back by the force of the explosion and is immediately closed by the return spring. Right here is the difficulty. The bolt opens and closes before there is time to release the trigger. Actually, it's faster than the eye can follow. As a result of this rapid movement, the sear is still held down by the trigger when the bolt is closed. Since there's nothing to catch the hammer, it follows the bolt forward, but it doesn't have enough force to fire the next round, and firing stops. In other words, a firing mechanism is needed that will stay cocked even though the bolt goes back and forth at terrific speed. First, let's build a typical firing mechanism for semi-automatic fire. Such a mechanism must remain cocked with the trigger held to the rear. It should fire when the trigger is released and then squeezed again. This can be done in a number of different ways. Here on our model, we've added a new sear of the same type as the first one. It is mounted so it can pivot independently of the trigger. Now, we'll mount a spring under the new sear to hold it up where it can catch the hammer. That doesn't completely solve our problem because we still can't fire the mechanism. We must be able to depress the new sear by squeezing the trigger. What is needed is a connection between the two sears. We'll put a link on the original sear. It pivots freely on a pin, but to keep it from pivoting too far, we'll put a stop lug on the original sear. Now the link always returns to its original position. The link is long enough to reach to the new sear, and to make contact with it, we'll put on another small lug. Now watch what happens. The hammer is held cocked by the new sear. When the trigger is squeezed, the link moves the new sear down, releasing the hammer. A fraction of a second later, the link slips off of the lug, and the new sear pops up to catch the hammer again. Let's see it again. The sears come down together, releasing the hammer. The new sear snaps up and catches the hammer, even though the trigger is still held back. To fire the next round, we must release the trigger. The link hits the lug on the new sear and pivots. After it passes the lug, it drops back into its original position, and the firing mechanism is ready to fire the next round. We now have a semi-automatic firing mechanism. Each time we fire, the bolt moves back and forth before the trigger can be released. But the new sear is up waiting to catch the hammer. Then we can fire the next round by releasing the trigger and squeezing it again. Semi-automatic fire. One shot each time the trigger is squeezed. To get automatic fire, we must arrange the firing mechanism so the weapon will fire continuously as long as pressure is applied to the trigger. We've seen how in semi-automatic fire, the hammer is caught by the new sear and held until the trigger is released and then squeezed again. But in automatic fire, the trigger will be held back, so we need a means of firing each time the bolt closes, even with the trigger back. That means on this mechanism, we must disconnect the new sear from the hammer each time the bolt closes. A part such as this disconnector will do the job for us. We've mounted it so that it can move up and down. As it moves down, it depresses the sear and releases the hammer. To move the disconnector each time the bolt closes, we'll put a lug on the bottom of the bolt. Now, as the bolt closes, the lug cams the disconnector, pushes the new sear down, and the hammer is released to fire the round. The bolt moves back and the lug clears the disconnector. The disconnector moves up and the new sear is in position to catch the hammer, even with the original sear held down by the trigger. The cycle starts over again, and the weapon will continue to fire as long as pressure is applied to the trigger. When the trigger is released, the original sear rises. Now, when the bolt disconnects the new sear, the original sear is up in position to catch the hammer and stop the firing. The hammer is held back, cocked, and automatic fire can be resumed merely by squeezing the trigger again. Now let's look at weapons which have both automatic fire and semi-automatic fire. These weapons have a lever to select the type of fire desired. These firing mechanisms are not much different from the ones we have just seen. All that's done is to arrange the disconnector so it can be shifted in or out of engagement with the new sear. With the disconnector out of engagement, the firing mechanism will give semi-automatic fire. One shot each time the trigger is squeezed. With the disconnector engaged, we'll have automatic fire just as we had before. That covers the basic principles for both semi-automatic and automatic fire. You'll find many different types of firing mechanisms on small arms weapons, but all of them have to perform the same operations we've pointed out to take full advantage of the speed and convenience of modern weapons.